Hello everyone. Today we are going to talk about kinetics of a rigid body. Kinetics is dealing with the forces that causing the motion. We talked about kinetics of a particle, and the equation that we use for kinetics of a particle was summation of forces equals ma. But today, because we are talking about a rigid body, that means that the rotation is also important. And what is causing the rotation? The moment. So the second equation that we need to write for rigid body is summation of moment I alpha. So we defined mass as the resistance to acceleration. We define I as the resistance to angular acceleration. So we can write resistance to angular acceleration. I is defined as moment of inertia or second moment of inertia. We have another I that we use in bending equation, and that's second moment of area. That's CI. So you need to remember that this I is not the same as the I that we are talking about. Here is an moment of area, depends on our geometry. Here, in addition to geometry, it depends on our density as well. I is defined as second moment. So if you have a mass here with a distance r, our I, moment of inertia, is defined as r squared dm. And dm is our differential mass. And we know mass is rho v. So we can write dm as rho dv, assuming that the density would be the same. So I is also written as r squared rho dv, where r is perpendicular distance z-axis, or the axis of interest. If you're finding your moment of inertia about z-axis, so r would be the distance to z-axis, and it's perpendicular distance, similar to moment equation. So we deal with this r squared rho dv, or in general r squared dm. So the unit system that we are going to use is either SI or FPS. If you're using SI, it's kilogram times meter squared, or if you're using British system or FPS, pound system, you have a slug at the unit of mass, and then foot squared. Now we are going to solve an example finding the moment of inertia for a cylinder about z-axis. Let's say this one is z, this one is y, and then this one is x. If our cylinder has a radius of r and height of h, we're going to find I for our cylinder. First, we need to define a differential element that I'm going to define a shell element. So our differential element would be a shell element. So we select a shell element with thickness dy and distance y from the axis. So if I draw my shell element here, let's draw it better here. When we are talking about shell, means we are talking about thin section. So that's the shell element that I have. And the distance here is y. Y is not equal to r necessarily. Y could be any value from 0 to r. Also, the thickness is dy. So now I'm going to write my moment of inertia equation. Di is r squared dm, or we said that we could write it as r squared rho dv. So we need to find dv here, the differential volume. The volume of a shell would be circumference times the thickness. So that would be 2 pi y, that would be circumference, times its thickness, that would be the area, times the height would be the our volume. So this shell goes down. It has a volume here. So now that I have, let me erase this so I could actually, now that I have my volume, I could replace it here. So I can replace dv here. So I get r squared rho 2 pi y h dy. And I have r. Here r would be y for me. So r squared, I can write y squared. So if I can write it here, the equation that I need to deal with is rho 2 rho pi h, and I have 1y here, y squared, so y cubed dy, and it's going from 0 to r. So I can write I 2 pi rho h y force y to the, and then 0 to r, which is simply 2 pi rho h r the power of 4 over 4, or if I simplify that, would be half of pi rho h r to the fourth. But I'm interested to write the moment of inertia based on the mass. So if I find a mass of the cylinder, the mass of the cylinder would be the area, it would be rho v, and then v would be the area, pi r squared, and then h. So if I use this in my equation, I find I to be half of m r squared. So instead of pi rho h here and r squared, I used mass and I get my I. So we know that the moment of inertia of a cylinder is mr squared. So if you're using a heavier material, your I is higher. If the radius is higher, also the I goes higher, and I is the resistance to angular acceleration, which means that a higher I would give us a lower acceleration given the same moment. Now we are going to talk about parallel axis theorem. So parallel axis theorem is saying that if the moment of inertia of a body about an axis is known, we can find a moment of inertia about any other axis. So about for the cylinder example that we talked about, if we know the moment of inertia about the axis z, and you want to find a moment of inertia about point z, about axis z prime, and we know the distance between the two is d, the parallel axis theorem is saying that iz prime would be iz, whatever we find about the axis v plus m, the mass of the cylinder, times d squared, and d would be the perpendicular distance between z and z prime. Let me write it here. So d would be the perpendicular distance between z and z prime axis. So as an example, let's say you have a disk with a center here O, the radius is R, and so let's call this center G, the center of gravity. Then you want to find the moment of inertia about point C. So if you have I, G, as half mr squared, usually the inertia is given about the center of gravity. So we have IG, and if you want to find IC, is IG plus the distance, md squared. And what is d here for us? The distance between the two, the parallel distance. D here is r. So I can write IC IG plus mr squared. And this one is IG is half mr squared. So at the end I have 3/2 mr squared. So with parallel axis theorem, if I have the moment of inertia about a point, I can find a moment of inertia about any other point. That helps us a lot in solving problems, that we could find a moment of inertia about different points of interest. The other definition that we're going to talk about here is the radius of gyration. So in radius of gyration is defined so we could report all moment of inertia using the same equation, calling all of them I equals mk squared. So for all different objects with different geometries, the moment of inertia is I equals mk squared. And then we report k for different geometry. As an example, if you want to find the radius of gyration for a thin square plate, we know for a thin square plate, let me draw square plate. You know about z-axis, the moment of inertia is the mass, 1/6 of the mass, a squared, where a is the length of our square. So instead of reporting it that way, I can report it using radius of gyration. So I can write IV is mkz squared, mk squared. And if I compare the two, then I can find that k is a square root of 6. So radius of gyration does not add anything or does not change anything to moment of inertia. It's just a new way of reporting moment of inertia. Instead of using different equation, usually in different books, they report moment of inertia as mk squared. And now for different objects, we have different k's. For thin plate, thin square plate, we have k as a over a square root of 6. And you can find the radius of gyration for different objects as well. And one thing that you need to pay attention is that the same way that we have different moment of inertia about different axes, we have different radius of gyration for different axes as well. The other concept that we're going to talk about here is composite bodies. If you have multiple bodies, the moment of inertia of the whole system would be just the addition or subtraction of each body. If we have a hole in the system, then the moment of inertia would be negative. But in general, for a composite body, that's the equation that we use. So if we have two objects, That would be I1 plus MD1, and then this is the parallel access theorem. If you want to, because different objects could have different moment of inertia about different axes. So we are going to bring all of them to the same axis. So I2 plus, let's call it M1, M2, D2 squared. And if there is a hole, then this value would be negative instead of a positive value. Now let's solve a problem for composite bodies. Determine the mass moment of inertia of a thin plate about an axis perpendicular to the page, so the z-axis, and passing through point O. So the trick of the problem is that we want I about point O. For a plate and a disk, usually the moment of inertia is reported about their center. So we have to use parallel axis theorem to move the center of the axis of rotation for us. So I-O is needed. We know that the moment inertia of the system is I of disk, because we have a hole here, minus I of square. But for each case, for disk and square, we need to move using parallel axis theorem. So I G about its center of gravity plus md squared for this. Same thing for square. So what I'm doing here, first I find the moment of inertia for the disk about the axis of interest, which is O. Also, I find the moment of inertia of the square about the axis of interest, O. So I use parallel axis theorem, and then I subtract them from each other to find the I of the composite body shown. So let's start with the disk. IG, the moment of inertia of the disk about its center of gravity is half mr squared. I need to use parallel axis theorem to move it to point O. Same thing for for the square about its center is 16 ma squared. I need to move it to r squared here. Now if I simplify it, that would be 32 mr squared minus, and a and r are the same thing. In this problem, you can see both of them are 200 millimeter is the radius, and a is also 200 millimeter, so it simplifies the problem. So a and r are the same thing, so I could write 76 mr squared. One thing that we need to pay attention is that here the mass of the two are different. Here we wrote the moment of inertia for the disk based on the mass of the disk. Also here is based on the mass of the square, and this is based on the mass of the whole disk. So this is the whole disk, this is the square, and then the subtraction. When we subtract the square from the disk, then we have our disk, our hollow disk. So these two masses are not the same thing. So it's helpful to use D and S, so we know the two masses are different. But we know mass is nothing but the density times a volume, so we could write it as function of density and volume. So 3/2, instead of mass, I write rho AD, the area of a disk, r squared, minus 76 area of the square, and I have rho r squared. The area of a disk is pi r squared, so that would be 3 rho pi. I have r squared here, another r squared would be r to the fourth, 6. I have rho, and then AS, the area of my square, is r squared because each edge is r, so that would be r forces as well. So I can simplify my equation here. Now rho r force over 2 pi minus 7 6. At the end, I get the answer to be, if I have rho, the value of rho is given in the question, that's the density, or if the radius is given, I know the value for pi, so 0.113, and the unit is kilogram meter square. So one thing that you need to pay attention here is that the density given as mass per unit area, because it's a 2D problem, and the length is not given, so that's the per unit length. So this density is sometimes given as mass per unit length, mass per unit area, and mass per unit volume, depending whether we are solving 1D, 2D, or 3D problems.